One of the most important things determining the usefulness of a telescope is its diameter, or aperture. A larger aperture allows a telescope to receive more light and also improve its angular resolution, the ability to see fine details. In this question, we'll calculate how big a telescope is needed to see the details in some of the galaxies in your constellation. In this question, we're trying to find the minimum size of telescope required to resolve details in galaxies. If the telescope is too small, the physics of light means that there's no way we can see any detail in the galaxy. While we could magnify an image of that galaxy, it would just get blurrier. Exactly how much detail we would need to see depends on what information we want to learn about the galaxy. In this case, we're assuming we need to see details as small as 1/50th of the size of the galaxy itself. If we're looking at galaxies the same size as our own Milky Way, which is 100,000 light years across, then we'd be seeing details as small as 2,000 light years. This is enough resolution to see broad structures like spiral arms, but not nearly enough to pick out individual stars. So one of the pieces of information we know is that we need to resolve 50 times smaller than the size of the galaxy. The other value the question tells us is the wavelength of light we're studying. We're observing in the near-infrared wavelength known as the K band, which is 2,190 nanometers. So you should also write down this value. There is just one thing you need to predict on this question: which galaxy requires the largest telescope to observe? To determine this, you're going to want to look at the angular sizes of the galaxies. Angular size is a measure of how much of the sky the galaxy takes up. The units we use for angular size are arcseconds. An arcsecond is a very tiny angle. 60 arcseconds make up 1 arc minute, and 60 arc minutes make up just 1 degree. Remember, it takes 360 degrees to make up a full circle. So your prediction should be based on which galaxy's angular size is going to make it hardest to observe in detail. That's the one that will require the largest telescope. Remember to explain your choice. The equation that relates the diameter of a telescope to the angular resolution is given by diameter equals 2.5 times 10 to the 5th arcseconds times lambda over theta. Don't worry about the 2 Greek letters in this one. Lambda, the one on top, is one we've already seen. It represents the wavelength of light we're observing. On the other hand, theta is the angular resolution we need to achieve. Another way of saying this is that theta is the smallest angular size of any detail we can see. So smaller angular resolution means you're seeing finer details. Since we already know the wavelength of light we're observing, the main thing we need to look up is the angular size of the galaxies we'll be calculating. Remember to do at least 3 of these, including the one you predicted would require the largest telescope. The arcseconds in the constant in the diameter formula tells us which units we need to use for the angular size. Fortunately, this is the unit that's given in the constellation table, so we're not going to have to convert that value. However, we do want the answer to come out in meters, not nanometers. So let's convert the wavelength into meters. To do that, we remember that the prefix nano means 1/billionth. So there are 10 to the 9th, or a billion nanometers in 1 meter. We can make a conversion factor out of the equation with the meters on top and nanometers on the bottom, since we want the nanometers to cancel. That gives us a wavelength of 2.19 times 10 to the minus 6th meters. Now let's calculate how big the telescope has to be. Let's assume the galaxy angular diameter is 125 arcseconds. We start by writing down the equation with the values in it. Notice that we've taken the angular size of the galaxy and divided it by 50. That's because we want to be able to see details that are 50 times smaller than the size of the galaxy itself. At this point, we do what the equation says. We'll take a couple of steps to solve the problem. First, we divide the angular size of the galaxy by 50 to get the angular resolution we need. Next, we divide the wavelength by the angular size and multiply through by the constant. The arc seconds cancel out here, so our answer is in meters. This result, 0.22 meters or 22 centimeters, is fairly typical of the sort of answers you should expect here. Finally, you should say if your answers make sense and match your predictions. Remember that if they don't match, the problem could be with either the prediction or the calculation, so you should discuss which you think is going on. If it's a problem with the prediction, you should say what you should have predicted and why. On the other hand, if it's the numbers that don't seem right, that probably means there's a problem with the calculation. For most galaxies, you should be getting telescope diameters that range from a little less than 0.1 to a little more than 1 meter. If it's outside of that range, then you should check your calculations. If you're stuck, feel free to ask for help.